Hi, this video is about volume flow rate. What is volume flow rate? Which means I'm using VFR for abbreviation, means how much volume it passes through per time. And often in textbooks, they are using volume flow rate, they are using V dot. Whenever we have a dot, it means it's derivative over time, right? That's V dot. That's like how much volume passed per time. And whenever I have a prime, this is just a quick, let's see. We learned about, y prime. That means dy over dx. That means derivative with respect to distance. When you have a dot, that means derivative with respect to time. Okay, so that's a little quick sidetrack. So volume flow rate, dot is divided by time, volume over time. So think about the unit. For SI unit, the volume will be a meter cube and time will be per second. So that volume flow rate will take a unit as meter cube per second. For US unit, that would be feet per second, cube over second. Okay, but we normally do not hear feet cube per second. Often we hear like a gallons per minute, right? Gallon, that's indeed a volume unit. Minute, that's a time unit. And also we hear about like CFM, like for HVAC system, like how much airflow, that means cubic feet per minute. That's also a volume flow rate unit. All those are volume flow rate unit. So another concept I want to go through is how is volume flow rate relates to velocity. So thinking about if you have this little pipe here, and we'll assume there's a velocity, and I'm using velocity as small v, okay? So this velocity, let's say it's 10 meters per second traveling through the pipe. And they want you to find volume flow rate. How do we do so? All right, this little quick thing, this cross section of this pipe is perfect circle, we'll assume. And if it's perfect circle, and we can look at the cross section, we see the radius, for example. Let's see if the radius is 2 meters, which is quite big of the pipe. So if that's a situation, how do we figure out volume flow rate? So here I would like to use dimension homogeneity to help us to figure it out, this relationship here. I don't think I spell homogeneity. No, I think it's right. Okay, so that means left side and right side, they have to have the same dimension. This is actually quick. This is a scale we're going to use a lot in engineering, dimension homogeneity. So for example, this volume flow rate, how is that related to velocity? There's going to be something we're going to times or divide. Let's think about the dimension on the left side. For volume flow rate, we're talking about if using SI unit, that would be meter cube per second, because that's how much volume it travels through over time per second. And velocity, we know it's or speed, it's distance over time. Distance is in meter, how much it travel meter per second. Okay, so to make left side and right side have the same dimension, what do we need to have for that question mark? That's right, so that will have to meter square, because this meter and times that meter square will give us meter cube, and they have the same for the bottom for second. So that's gonna be the missing link. So what dimension will have the unit of meter square? That's right, it's gonna be, well, area. So here's a relationship to relate velocity with volume flow rate is through this cross-section area. So velocity times cross-section area give us volume flow rate. Okay? So we can do a quick example on this. For this pipe example we just did, let's figure out the volume flow rate for this problem. It's going to be velocity times cross-section area. Velocity is given as 10 meters per second. And our area is going to be this cross-section area, right? Well, that's perpendicular to this velocity speed. And that's going to be pi r squared. And here r is going to be 2. So it's basically 2 squared. And then we can quickly, and that gives us unit of meters square, right? Because it's area unit. And when we plug it in, we'll get 40 pi. Meter, it's going to be meter cube per second for volume flow rate. And so that would be, given the velocity, you can find the volume flow rate. A quick example on that. Okay, so here I want to introduce another concept through this example. So if you have often in reality you have pipe that's going to be tapered or enlarged, downsized or upsized. So for example, this is going to be downsized here. Okay, so you have this type of connection. You have a bigger pipe and then connected to the smaller pipe. And let's say this bigger pipe, it's 12-inch. And this smaller pipe is, let's see, 3-inch. Okay. And there's a fluid passing through here. And right here, we'll call this as 10 foot per second. That's the speed. That's a V1. Then, given this dimension, you want to find what is going to be the speed traveling at within this smaller pipe. So let's think about, based on our intuition, do you think they're going to have the same speed? Probably not, right? Because if a smaller pipe, they have smaller area to pass in through, they have to go faster. When you think about, you squeeze a garden hose and you restrict the area, and do they come out very quicker, much quicker? Yeah, so the velocity here, based on your intuition, must be increased, must be more than 10 foot per second. But how much more? So for this problem, we can use this volume flow rate to help us figure it out. Because this big V dot volume flow rate for this pipe 1 is gonna be equal to volume flow rate in pipe 2. Why is that? That's because mass conservation. They have the same amount of mass passing through every single time. Because this pipe is rigid, it's not like bulging out or small, becomes narrowed. So they're gonna have the same mass flow rate, and because it's the same uniform fluid, so volume flow rate will be the same. So knowing that will help us figure it out. We just said volume flow rate is velocity, V1, over cross-section area of A1. That's our A1. And this will be our A2. Okay. And then here, volume flow rate, that's going to be equal to velocity V2 times cross-section area A2. So knowing that, we can go ahead and put our radius in there, or diameter in there. So velocity times pi r squared, r1 squared, and velocity times pi r2 squared. So pi and pi canceled out, right? Then what's left? If we're solving this V2, we can just isolate V2. V2 is going to be equal to r2 squared and V1 r1 squared. Then we can potentially write down V1 times R1 over R2 square. So that is something you have derived based on the mass conservation and volume flow rate definition, and how is that related to velocity. What we're solving this final speed. We know it's going to be greater. How much greater? I think we're about to find out. So V1 is 10 foot per second. And R1, what's the radius of R1? That would be 6, right? And what's the radius of smaller pipe? It's 1.5. And so that's basically a ratio of bigger pipe over smaller pipe. That's a ratio of 4, right? 6 over 1.5 is 4. But don't forget, we have to do what? That's square, you know? So that means it's 10 times how much? 4 squared, that's 16. So V2 is greater than V1. How much greater? 16 times more, 160 foot per second. So if you know this in the future, you can just quickly look at the dimension. You said, okay, that's 12 over 3. That's a ratio of 4, but we're going to square, so that's going to be 16. So then the velocity here, V2, will be 16 times more than that. So it will be 16 times 10, 160 foot per second. All right, so that's going to be the major concept for volume flow rate. Okay, we start with the definition and the unit, and we learned about how that's related to velocity, and we apply to a real life example using mass conservation. All right, I'll see you next time then. Bye now.